So we're going to switch gears for just a second and talk about how tensors transform under a rotation. So before, when we were talking about strain and the deformation gradient, we defined a rotation tensor, right? So if you have an axis or a basis that's u, and say this is u prime, and this is v, and this is v prime, right? Then we can write down the direction cosines according to some angle and come up with a matrix equation, or right, that's like u prime r u and v prime r v. And we did that, right, when we were talking about rotations with respect to strain. And we actually put in some values there, direction cosines. But here we'll just call it R. It's a unitary rotation matrix, okay? And so what we're interested in is what happens to a tensor, right? So if we have a tensor T and we undergo a change of basis, okay? So say we have that V is equal to TU, right? So tensor would just be, this T would just be the linear operator that takes U into V, right? And we want to know what happens to T when we change the basis, right? So if we change the basis so that we have something like this, the question is, how are T and T, I'm sorry, this should be U prime. So V prime and U prime. So when we have a change of basis, how does T prime and T relate to one another? So in order to figure that out, let's just plug in what we had for our vectors, right? So U prime is RU. So we have, and V prime is RV. So we have RV, T prime, RU. All right. Now if we multiply on the left-hand side by R inverse on both sides of the equation, right? Any matrix inverse times itself is the identity matrix. So we have IV R inverse T prime R U, right? And of course, the identity matrix times any vector, then we have V equals R inverse T prime R U, okay? And we said, or we showed before, that a rotation matrix is unitary, so that means its inverse is its transpose, right? So we can likewise write this equation as R T prime R U, okay? So now if we just compare this equation and this equation, just by inspection, then you can see that T must equal RT T prime R. And so then if we have that, we can come up with the inverse relation to that by just, if we multiply on the left by R, and if we multiply on the left by R and on the right by RT, then what we'll get is that T prime is equal to RT R transpose. So that's how a tensor transforms under a rotation. And in fact, we won't go into it, but if you look in sort of a math textbook or definition where tensors are introduced, it's this very relationship of how they transform under rotations that defines them, irrespective or when compared to like just a matrix. So when a second order tensor, a lot of times we just use it like it's a matrix, right? But when you go higher order, third order, fourth order tensors, they're not matrices, right? So second order tensors sort of tend to obey matrix vector operations and other things. But when you go higher order, they're not. And it's this very property of how they transform under rotations that sort of gives them their definition. We won't really go into it. I won't say anything else but that. Okay. So